new seminar today. And today we will have the talk by Dr. Thea Kozakis. She's a postdoc here at the IAA. She will talk about ozone and search of life for life in the universe. So Thea Kozakis is an astrophysics and astrobiologist. Currently working here as a Severo Ochoa postdoctoral fellow. And she's particularly interested in using photochemistry and climate modeling to study how we could use ozone, as a biosignature in search of life in the universe. She completed the PhD work at Cornell University with Carl Sagan Institute. Her PhD thesis last called for life, habitability for terrestrial planets orbiting red giants and white dwarf. Focuses on combining stellar evolution and astrobiology to study planetary habitability for systems with host of variety of masses and ages. She got her start in astronomy doing observational research with Joe Carson at the College of Charleston on direct imaging of exoplanets around high-mass stars with the Subaru Seed Survey. After she got the PhD at Cornell, she spent 4 years in Denmark as a postdoc at the National Space Institute at the Technical University of Denmark with the exoplanet. Also, her current research focuses on exoplanet habitability and origin of life. She's interested in a variety of different areas in astronomy research. So thank you, Thea, for this seminar, and the floor is yours.
All right, thank you so much. Can everyone hear me okay in the back? If someone can't hear me at any point, just wave, do something. Tell me if you can't hear me, it's Louisa. So yes, I'm Thea Kozakis. So my grandparents are Greek, so I actually pronounce my name like Thea, sort of like the end of Thea. But I respond to anything that sort of sounds like my name. So today I'm going to talk to you all about a project I've been working on the last few years, which involves thinking about ozone and its role in our search for life in the universe. But to start off, let me see if I could get this to work. Of course.
Click on the screen.
Click on the screen first, do you think?
No.
There you go. Now try it. Okay, so this may or may not work. So I did have the nice introduction, but to start off, I wanted to let you all know a little more about what I'm interested in general, because part of why I wanted to give this talk was to let people at the Institute know what it is that I'm doing, because I would like to find some collaborators in the Institute. And I've worked on a lot of different projects and I'm interested in a lot of different things. So I settled on showing you what I call my science vision board. So the idea is you could just sort of look at this, and if there's anything on this board that you also work on and would like to work on with me, let me know. So I'm really interested in UV light in general, how it interacts with planetary atmospheres. I'm very interested in all types of stars in terms of being exoplanet hosts. So stars of different ages, different types, different sizes, everything. And I'm interested in all different sorts of rocky planets. So I'm very interested in Earth, but I'm also interested in Venus. I'd like to try to start modeling Venus soon. And I'm also interested in using my modeling to be relevant for current and future missions. So if you're interested in any of this, or in the rest of my talk and want to collaborate, please send me an email or just talk to me afterward. And send me your science vision board if you want to. You don't have to. You could just send me a normal email. But anyway, let's get started on what I'm going to talk to you about today. So Renee mentioned that I describe myself as an astrophysicist and an astrobiologist. And astrobiology is an interesting field. So there's a lot of people in it because it's basically anything that pertains to the search for life in the universe. So we have physicists like me, we have chemists, we have geologists, biologists, and we're all just trying to figure out how to look for life in the universe. And I do think it's funny that astrobiology is the only field where you could do statistics on a sample size of 1, and somehow it's called scientific. Because although we know there's a lot of exoplanets in the universe, we're finding a lot of diversity there, Earth is still the only place that we know life exists. So we can imagine all sorts of life, but Earth is all we know of right now. So that's why my work is primarily focused at the moment on Earth-like planets. And I think of it approaching the search for life in the universe sort of as I think about doing a jigsaw puzzle. So when I do a jigsaw puzzle, I like to start with the edge pieces because they're really well defined and I know exactly what I'm looking for. And I figure when thinking about life in the universe, let's start with what's more well defined and we know what we're looking for. Because if we can't even find Earth-like life in the universe, the one life that we understand allegedly, we should start off there before moving on to the more exotic inner pieces of the puzzle. So can people see this okay? Is the light okay? Or can we maybe turn off the lights? It's okay if you fall asleep if the lights are off. Or these lights? How do these work? This room is so fancy. Wow. Now if you fall asleep, no one will know except for me. These chairs are really comfortable. I will not blame you. It's been a stressful week. All right. So when we think about Earth-like habitability, you probably think first of the habitable zone, which you could see here in green for our solar system. So the habitable zone is very simple. It's just the region around a star where liquid water could possibly exist on the surface of a planet. I give a lot of outreach talks, especially to young children. And even when I show this diagram to young children, even they could see that this is not a great judge of if a planet is habitable. Because we have Earth in the habitable zone, but Mars is also in the habitable zone, and Venus is almost in the habitable zone. So even when I ask little kids, like, do you want to live on Mars? They're like, no, they don't want to live on Venus either, because this is not a great way of telling if a planet is habitable. I think the habitable zone is a nice tool for us to maybe think about exoplanet candidates we're finding, but it's not the full story. The full story looks a little more, let's see if we go to the next slide. It looks a little more like this. Has anyone here seen this figure before? Oh, great. It's new to all of you. I get to show you the scary figure first. So this is informally referred to in the astrobiology community as the planets are hard figure, because planets are hard. There's a lot of things you need to think about with planets. You need to think about the whole planetary system they're in. You need to think about the star. And then the planet itself is quite complicated. And if we want to think about habitability, we need to think about everything on the planet, not just the atmosphere, but also the surface and the interior. No mortal person could really be an expert in all of this. So a lot of astrobiology is just picking a part of this figure and doing the best that you can. Where I live on this figure is mainly thinking about the host star, especially the UV spectrum of the host star, along with the atmosphere of the planet. All right, I'm just going to give up on this clicker. We tried. So thinking about the atmosphere of the planet, if you're thinking about life in the universe, usually you're talking about biosignatures. And biosignatures are just signs of life in the atmosphere of a planet. If Earth didn't have any life on its surface, the atmosphere would be really different than it is now. Because right now we have all this life on the surface. We have vegetation. It's creating most of the O2, almost nearly all of the O2 we see in the atmosphere. And the vegetation is also sucking in CO2. We have livestock that's creating methane and consuming the O2. And we have humans that are using up O2, creating CO2. Maybe the life on this planet is creating a little too much CO2. Who knows? But the main point of biosignatures is just if you look at a planet with life on the surface, the atmosphere and the life are not totally separate. They're They're working together here as we are with our atmosphere. And the idea is, let's look into the atmospheres of other exoplanets and see if we see signs of life. One of the most popular biosignatures is oxygen, molecular oxygen, O2. However, if we just see O2 in the atmosphere of an exoplanet, we don't know for sure if it's from life. Here on Earth, most of the O2 in the atmosphere is from vegetation, but we've discovered that there are some ways for O2 to build up in the atmosphere of a planet in non-biological ways. So what we propose is to look for a disequilibrium biosignature pair. And we talk a lot about O2 along with the reducing species like methane, something that could convince us more that these things are being created by life. And to explain this, we have a fun analogy we like to use in the astrobiology community, which is O2 and methane are like PhD students and pizza. And I will explain this. So here you can see a picture of some PhD students with pizza. This was me with back in my younger days when I was a PhD student. And you can see that we have pizza. And without any more context to this image, there's only a few possibilities that you know could have occurred here. Either the students just got there, the pizza just got there, or someone is continuously supplying the pizza. Because this is not a steady state. The students are going to consume the pizza. And if you had taken a picture of us just a few minutes after this photo, there would have been no more pizza. And you could think of O2 and methane like this as well. The O2 is going to consume the methane and vice versa. So if we were to see both of them in the atmosphere of a planet, that means that they're both being replenished by a surface flux of O2 and methane. And so far, the only thing that we know that could have such a strong surface flux of O2 and methane is life. Is everyone with me so far? If anyone has a burning question, please feel free to raise your hand or shout or something. All right, so you might have noticed that the title of my talk doesn't have O2 or methane in it. It is about ozone. And what I'm studying is how ozone fits into this. Now, ozone, it is my favorite molecule, and you'll know that by the end of this talk. Ozone is the photochemical product of O2, and it's the main shielder of UV on our planet. I'll give you my favorite ozone fun fact, which is if you were to condense the entire atmosphere to standard temperature and pressure, you'd condense the atmosphere down to about 8 kilometers. And of that 8 kilometers, the ozone, all of the ozone in the atmosphere would be only about 3 millimeters tall, which when I was in the United States, I was able to say, it's like 2 pennies. So I was Googling the, thickness of a euro coin. It would be less than 2 euro coins together. It's small. So even though ozone is what's allowing us to be here and not be irradiated by harmful UV, there's almost none of it in the atmosphere. Yet it absorbs really well in the UV. It's amazing. And the reason why it's relevant to biosignatures isn't just because it shields surface life, because life on Earth started before there was a lot of O2 in the atmosphere, before the ozone layer. It's possible you could have planets with life happily living under the ocean, and it doesn't care about if there's UV shielding. But if we want to think about the O2 methane biosignature that I mentioned, some people are quite interested in ozone because there are a few scenarios, possibly common scenarios, where ozone is going to be easier to detect in an exoplanet atmosphere than O2. Let me give you a few examples. One is in the mid-infrared. There are a few proposed missions that want to look for biosignatures specifically in the mid-infrared because there are a lot of nice spectral features of possible biosignatures there. However, there are no O2 spectral features in the mid-infrared. All of these missions that I've proposed to do this are already saying that they're going to look for ozone and methane together, even though ozone is not directly produced by life, because there's a nice ozone feature in the mid-infrared. And another important thing when thinking about O2 is that for most of Earth's history, O2 levels were not like they are now. So here's a nice plot. It's not my plot, it's from a paper, and I enjoy this plot quite a lot. So it's showing us a few different things. It's showing us over Earth's geological history, not only how the atmosphere and the O2 content has changed, but also how the biosphere and the geosphere have changed. So the bottom panel here, we could see how O2 changed over time. It's measuring O2 in terms of PAL, which stands for present atmospheric level. And you're going to see this abbreviation throughout the talk. So you could try to remember it. I'll try to say it out loud as much as possible. And you could see that on early Earth, the bottom is measured age in GA, which just means billion years ago. Geologists love to use GA. So 3 billion years ago, we had an anoxic atmosphere. There's very little O2. And then you could see there were little O2 whiffs. They always call it that. When we had cyanobacteria discover how to use photosynthesis to create O2. Finally, there was the great oxidation event about 2.5 billion years ago. And there, this plot uses this name that I love, where they call this period of the Proterozoic the boring billion. So there was life on Earth, widespread life. There wasn't a huge amount of O2, but there was enough to have a pretty good ozone layer and UV protection. But then about 500 million years ago, we had a second oxidation event. There was more O2 in the atmosphere. It rose more to the levels that we see today. And that's when plants and animals started to take over the surface. And you can see here that O2 levels have only been at modern levels for about 500 million years, which when you think about the whole lifetime of the planet, is not very much. And you could see in the other panels, you could see how life was evolving. It was really around when we had the great oxidation event that we were able to have more complex life. The more O2 you see in the atmosphere, the more it allowed complex life on our planet. And the top panel, I think, is quite cool. It shows during these periods of time which supercontinents were there. So I'm not one of those people that remembers every single supercontinent we have, but we probably all know Pangaea. And we think of that maybe as a long time ago, but really in terms of Earth's history, it was just yesterday. So when we want to look in the universe for different planets that might have life, if we're thinking about Earth-like planets, we have to remember that Earth did not look like how we know Earth for most of the time. And if we want to think about O2, we need to remember that O2 levels were a lot lower. To drive home this point, here are two reflectance spectra of Earth-like planets. And on the bottom, we have modern Earth, and on the top, we have Proterozoic Earth. So Proterozoic Earth was mainly during that boring billion, where O2 levels were a bit lower. And you can see on modern Earth, it's pointed out some interesting O2 lines there. But if you look up at Proterozoic Earth, they are simulating two levels of O2 because there's some inconsistencies in the data. We don't know exactly how much O2 was there. So they do their models for 0.1 our present atmospheric level of O2 and 1%. And even for the 1% level of O2, you might be able to see there's a little tiny O2 line there. But even for the lowest levels of O2 that they simulate, you could see the big ozone UV feature, because ozone absorbs very well in the UV, which is why the ozone layer protects us from light. So if we did find a planet that was like Earth, but like Proterozoic Earth, looking for ozone instead of O2 would be a lot easier for us to detect. And the proposed solution to this problem of O2 being inaccessible in a lot of scenarios is let's just use ozone instead of O2, because ozone is created by O2. And this is something that has been proposed for decades now. And then I came in a few years ago and I asked, but how reliable of a proxy is ozone for O2? If we get a measurement of ozone, how much does this really tell us about the O2 on this planet? I had noticed that there were no studies that specifically looked into the O2 ozone relationship, especially around different types of stars. So I decided I would do it myself. And you're going to see how that went in this talk. So to start off on this journey, I should first tell you how ozone is created from O2. And these two reactions are the main ways that ozone is created in the stratosphere. So you have an O2 molecule. It's hit by a photon. The photon has to be less than 242 nanometer in order to break apart the O2 bond. From there, you get oxygen atoms, and those oxygen atoms can then recombine with an O2 molecule with the help of a background molecule, which I've labeled here as M. The background molecule needs to take away the excess energy, and then you form ozone. This might seem pretty simple, but I would like to direct your attention to the fact that this second chemical reaction here that creates ozone, it is a three-body reaction. And three-body reactions are more efficient at higher pressures in denser parts of the atmosphere. And this particular reaction is quite temperature dependent. So this reaction is much faster at cooler temperatures. So I'll remind you of this later on. I just wanted to give you some foreshadowing for the rest of this talk. Another thing that's very important here is the dependency on UV to break apart the O2. We've known for decades that ozone and O2 have a nonlinear relationship, but especially if we want to start thinking about planets around different types of stars, this is going to be really important because not every star has UV like our planet. So another complication. In order then to really think about how ozone would form on planets around different types of stars, this requires then a lot of atmospheric modeling. So I use the code Atmos, which is a publicly available climate and photochemistry code developed by the Virtual Planet Laboratory. And I give it information about the host star, the initial planet composition, and then the climate and the photochemistry code will iterate back and forth until they agree that for this distance around this star, this is what the temperature profile of the planet would look like and the atmospheric composition. Once I have converged atmospheric models, I then use Picasso, which is another publicly available code. This one does radiative transfer. And for these models, I simulated the emission spectra of these planets to get an idea of what ozone observations would be like in the mid-infrared, because that's something a lot of people are interested in. So for my first paper that I wrote on this subject, there are multiple papers. I'm very interested in this. All I did was I had different Earth-like planets. And when I say Earth-like, I mean it's the size of Earth. I start with Earth's initial composition. From their host stars, I have them at the Earth equivalent distance. So they're receiving the same total amount of flux as we do here on Earth and should have the same surface temperature. And all I did in this first paper was I changed the amount of O2 in the atmosphere. And I varied the O2 levels from 0.01% to 150% our present atmospheric level to see how ozone abundances would respond. I'll start you off by looking at the results for the Earth-Sun case. Here you can see we have the plot. On the y-axis, we have the total ozone abundance. And on the x-axis, we have the O2 mixing ratio, which is just the fraction of the atmosphere that is O2. I've also put in these vertical lines showing some O2 levels of note. So you can see 100, 10, 1, and 0.1% are present atmospheric level of O2. So 100%, that's just modern Earth. And you can see right away that indeed the relationship between O2 and ozone is nonlinear. And what I find quite interesting is that if you compare the amount of ozone in this planet, which is supposed to just be modern Earth, if you compare between our modern levels of O2 and then only 10% the amount of O2 that we have, the amount of ozone is about the same. It's actually a little more if you only have about 10% our present level of oxygen. And that might seem a bit odd at first, considering that ozone comes from O2. But it basically boils down to the fact that when you take O2 out of the atmosphere, ozone forms deeper in the atmosphere. And to explain this, we'll do a nice little example here. Let's imagine two atmospheres. They both have the same exact background gases, but one has 100% our present level of O2, and the other one has only 50%. So if we think of the one with modern levels of O2, I'll add in some lines here to symbolize UV light coming in and breaking apart O2 in order to form ozone. If we think about this again in an atmosphere with only half the amount of O2, because there's less O2, the UV can go deeper into the atmosphere and form ozone deeper in the atmosphere. Are people with me? Good nod. Okay. People don't look so scared. Sometimes when I give talks to physicists and I start talking about chemistry, people get really upset. So I hope you're enjoying the chemistry. Anyway, the reason that this really matters is, again, this three-body reaction. You need that background molecule to carry away extra energy when forming ozone. And this three-body reaction is pressure dependent, which means when you take away O2 and ozone forms deeper in the atmosphere, it's forming in denser regions of the atmosphere and it forms more efficiently. So when we think back to this plot, when we're taking away the source O2, it doesn't matter at first for certain levels of O2 because you're taking away the source O2, but ozone forms deep enough that it's so much more efficient that actually for the Earth-Sun system, you would expect the maximum amount of ozone at only about 25% our present atmospheric level, which is, I think it's fun. It's okay if you don't think it's fun. But don't worry, we're going to add in more stars now, even more fun, if you're me. Like I mentioned before, Earth would look different around different types of planets, even if we literally took our planet and put it around a different star at a distance where it's getting the same total flux as we get here on Earth. The UV spectrum from the star is different, which means the chemistry is going to be different because we have different amount of UV coming in, breaking apart molecules at different rates. What I did was I did these models where I changed the O2 levels for 5 different host stars. You could see the UV spectra there. So I go from early G to mid M. And I wanted to see how ozone formation would change around them. Because again, there's a UV dependence there. Now, we were just looking at this. So here's the Earth-Sun system. But let's see what this relationship between ozone and O2 looks like for our other hottest stars. So here's the G0 and the K2. So you can see at first glance, obviously, there's different amounts of ozone for these stars, which makes sense if you look at the UV spectra. There's different amounts of UV, which means different rates of O2 photolysis forming ozone, but they have trends. And for all of these host stars, we all get the effect where the peak amount of ozone would happen at O2 levels less than modern levels, because again, less O2 means ozone forms deeper in the atmosphere more efficiently. So that makes sense. But then let's look at our 2 coolest host stars, the K5 and the M5. And you could see right away that those are different trends. Unlike for the hotter stars, for planets around the K5 and M5 hosts, when you take away O2, you're taking away ozone. And the reason for this is simply this: there's less UV coming into these stars, so ozone formation happens differently. If we return again to this toy atmospheric model we were looking at, if we want to imagine here that this is a planet around a star with less UV, we could just take away some of the lines. So simply these planets around the K5 and M5 hosts, they just don't have enough UV to go deeper into the atmosphere and experience that increased ozone efficiency of formation. How are people feeling? You could just give a facial expression. All right, I saw someone smile, thank you. So basically, we really do need to, if we're going to think about ozone around different types of planets, and if we want to use it as a biosignature, we really need to understand the UV spectrum of that star. That's going to be most important. But also, it's going to matter what the composition of that the atmospheric composition is going to look like. The results I was just showing you, again, I was just varying the level of O2 in the atmosphere. But the O2 abundance is not the only thing that affects the ozone abundance, because we have what we call catalytic cycles in Earth's atmosphere, and they're destroying ozone. And they have this form where on Earth, the two main catalytic cycles take this form, and X is usually OH or NO for the hydrogen oxide and nitrogen oxide catalytic cycles. If I were to model a planet with humans that were not taking care of the ozone layer, I would also put in catalytic cycles with chlorine and other pollutants. But in my models, at least so far, there's no humans or humans that have their act together and care about the environment. So not Earth. Anyway, so we have these cycles, and what's important here is you could see in the first reaction, we create XO, that powers the second reaction. And then in the second reaction, you create X, and it's created there. So basically, these catalysts, which we are representing as X, don't get consumed in this process. So they cycle back and forth, and they can keep reacting with ozone and oxygen atoms. And the net result is that you're turning oxygen atoms and ozone into molecular oxygen. And this matters because this is considered a true loss of ozone. So ozone is being hit by UV photons all the time in our atmosphere and being broken apart, but that's not considered a true loss of ozone because ozone gets broken apart into an oxygen atom and O2, and it just recombines again. However, if you're taking oxygen atoms and ozone and turning them into O2, you're sort of restarting the cycle of ozone formation, because the toughest part of forming ozone is having those UV photons of less than 240 nanometers. And this catalytic cycle sends it back to this point. And my question, this is what my second paper is about, is if I were to change some biological fluxes on the surface that power these catalytic cycles, how would the relationship between molecular oxygen and ozone change? And I'm going to share some results briefly with you. I'm going to look at, in the paper, I changed the fluxes of methane and nitrous oxide on the surface of the planet. Both of those are biologically produced. But I'm going to walk you through some results for when I changed the methane. And methane is important here for ozone because methane is what creates hydrogen oxides, which destroy ozone. However, the main direct source of hydrogen oxides is water. But water cannot freely travel into the stratosphere. If you have water on the surface, it can't go up into the stratosphere because our atmosphere has a cold trap, which is great for us because the water doesn't escape to the stratosphere and get photolyzed and leave. However, you can still put water in the stratosphere if it comes from methane. So in Earth's atmosphere, the main source of water is from methane. And I could have just shown you lots and lots of chemical reactions, but I decided for the sake of time and sanity, I was going to sum it up for you here. And if you want to see all the chemical reactions, you can read my paper or just talk to me about it. All you need to know is that the gist of it is if you have a methane molecule in the atmosphere, given enough O2 and UV light, every methane molecule can be converted into 2 molecules of water. And from water, you create hydrogen oxides. And the hydrogen oxides, as I mentioned before, will destroy ozone. And when they destroy ozone, they don't get consumed themselves. So they're very good at it. And what I wanted to know was what would happen if I increase the amount of methane in the atmosphere? And I'll show you some of the results here. So when you look at this figure, it's not filled in yet. I saw some people look confused. Every column here is a different amount of O2, again, in terms of present atmospheric level. And every row is going to be for a different host star. And what I was thinking about here was not just the absolute amount of methane, not the absolute amount of ozone, but whether when you add in methane, will it cause more ozone or less ozone than if there was modern amounts of methane. So red in this chart means that adding methane increased ozone, and blue means that it decreased it. And let's look first at the results for our two coolest host stars. These went mainly how I had initially expected. For all of these stars, they're all blue, which means that for all of these cases, when I added methane to the models, there was more methane in the atmosphere, which meant more water, more hydrogen oxide, and ozone was destroyed. However, as with most of the things in this project, I was surprised by the results around the hotter stars. As you can see, for our three hottest host stars at modern levels of O2, when I added methane to the models, it actually resulted in more ozone, which I will admit I was really confused about when I first ran these models. Because again, methane should be creating things that destroy ozone. However, there is another effect here. Like I mentioned before, if there's enough O2 and UV in the atmosphere, methane is created each molecule to 2 molecules of water. And what happened is, for these hotter stars with high O2, there was a lot of water in the stratosphere. So here's a similar plot, but what I'm showing is the amount of water in the stratosphere. So the redder it is, the more excess water when I added methane. And that makes sense, right? Because methane turns into water. But what's important to note here is how it affected the temperature of the atmosphere. Here we have the average stratospheric temperature compared to cases with modern amounts of methane. And as you could see, these cases with a lot of excess water in the stratosphere resulted in stratospheres that were cooler. And that might seem also a bit strange at first because we know water is a greenhouse gas. And here in the troposphere, when we have more water, we get hotter. However, up in the stratosphere, it's a lot thinner there, which means that instead of the heat radiating off of water being trapped, close to the surface of the planet, it's radiating out into space. So it's similar to CO2 cooling that we have in our atmosphere from climate change. And according to my models, which makes sense from what we know about all this, if you did have enough of an excess of water in the stratosphere, you would have stratospheric cooling from water. And the reason this matters is because changing the temperature in the stratosphere really affects both ozone formation and destruction. First of all, the three-body reaction that creates ozone is very dependent on temperature, and it's much more efficient at cooler temperatures. So these hotter host stars at high O2 levels, ozone is forming much faster. And not only that, but the catalytic cycles that destroy ozone are also much slower during cooler temperatures. So we have here, when we add extra methane to the atmosphere, for these hot hosts with high O2, with the stratospheric cooling, ozone forms faster and it's destroyed slower. And this demonstrates really well that it's not just photochemistry modeling that's very important when thinking about ozone. You also do have to do climate modeling as well, because the temperature in the atmosphere really determines how fast ozone forms and how fast it's destroyed. And I hope at this point in the talk, I have convinced you that the relationship between O2 and ozone is quite complicated with all this happening here. But the last thing I want to talk about is, how does any of this translate into observations? As someone who's doing modeling, I can model all of these fun things, but what will we actually see when telescopes are able to fully characterize these types of planets? So for these models, I mentioned much earlier in the talk that I modeled the emission spectra of these planets to look specifically at the 9.6 micron feature of ozone, which is a feature that a lot of future missions that want to look for biosignatures want to look at. And here we're going to look at what I have for models of Earth around the sun. So right now we have the ozone feature for just 0.1% our present level of O2. Here I'll add on for 1% our present level of O2. It's a deeper feature. That makes sense. There's a lot more ozone when you increase the O2. However, when we go to the feature with 10% our present level of O2, you could see it's nearly overlapping with the 1% feature, which is maybe a bit strange at first glance because the case with 10% our present level of O2 is a lot more ozone. And then let's add on modern Earth, where you could see that feature is a lot more shallow. And although this might seem strange at first glance, it makes sense when you think about the fact that emission spectral features, the depth of them is determined by the temperature difference between the emitting and absorbing layers of the atmosphere. So when we're thinking about ozone, we're thinking about the temperature difference between the surface of the planet and the stratosphere. And to explain this better, here are the temperature profiles for the cases with 100% our present level of O2, so modern Earth, and then just 1%. And you can see the black line, which is modern Earth. We have this stratospheric inversion there, and that is because of ozone, because when ozone is absorbing UV and protecting us from UV, it's heating the stratosphere. And conversely, even though this means there's a lot more ozone in the atmosphere than compared to the 1% case, this means the temperature difference between the surface of the planet and the stratosphere is less than the case like with 1% our present level of O2, where the temperature difference between the surface and the stratosphere is much greater, giving us a greater feature depth, even though that's simply because there's no ozone there heating the stratosphere. Again, it's a bit odd when you look at it at first, but we can understand it when we look at this. And of course, this is really dependent on the type of host star. So let's look at this for an M dwarf. Lots of people love M dwarfs. They're small, easier to see planets around. And here is the ozone feature in the mid-infrared for 0.1% our present level of O2, then 1%, 10%, and 100%. That might have seemed a little underwhelming considering everything else I've shown you in the talk is very nonlinear, but this one is actually a lot more straightforward. And that's because if you look at the corresponding temperature profiles for modern Earth levels of O2 versus only 1%, it's because you don't have that stratospheric inversion for M dwarfs, even with modern levels of O2. And this is because not only is there not a lot of ozone there, but because there's not a lot of UV coming in for the ozone to absorb. So even if you had an atmosphere with a lot of ozone, if there's no near UV wavelengths coming in for ozone to absorb, it's not going to heat the stratosphere. And because we don't have the temperature inversion, it actually means there's a much higher correlation between the amount of O2 and the amount of ozone and the depth of the spectral feature if you're thinking about emission spectra. So another thing to think about. And now that I'm reaching the end of the talk, let's just recap. We're going to have to care a lot about what the figure type is. Sorry, the spectral. Oh my God, I forgot what I was saying in the middle of the sentence. Sorry about that. We're going to have to care a lot about what the spectral type of the host is. Now, to recap, the question that I was answering was, is ozone a good proxy for O2? And first, I'll just remind you, why is it that we care about using ozone as a proxy for O2? It's because in the mid-infrared, where we want to look for biosignatures, there's no O2 features. And then also, if we want to think about Earth throughout time, O2 is very difficult to detect at low levels, whereas ozone can be detected at trace amounts. And again, this is actually the title of my paper. The journal told me to consider changing my title to not be a question, and I considered it. So what is the answer to this question? After all of my work that I've been doing, I confidently say the answer is that it's complicated. And I think you'll probably all agree after this talk. But I think that we can begin to understand the relationship between ozone and O2 well enough to start thinking about using it as a proper proxy for biosignature searches. But we will need to understand the UV impact on the host, on the planet from the host star. we're going to need to understand how different atmospheric compositions will affect ozone. I gave the one example with methane, but there are lots of other gaseous species in the atmosphere that can affect ozone. And we're going to have to think about the temperature profiles of these atmospheres, especially if we want to look at emission spectra. And with that, I will take questions and I'll leave you with this, which is the word cloud of the 2 papers that I've written on ozone. So you could just zone out and see that I really like using O2 and O3 in models. And yeah. Thank you.
Nice talk. Questions for Thea?
Explained it all perfectly, I guess. Yeah.
So thank you very much for the talk. It was super nice and very pedagogical. So thank you for
Okay.
because it's out of my expertise, so it's very
I try.
to see and understand a bit. But it's a bit depressing because we're investing quite a lot of time in James Webb to observe TRAPPIST-1 planets.
Yeah.
And according to your computation, it's actually totally out of any possibility.
Oh yeah, we're. Sorry, continue your question. Continue your question before I'm.
I don't know how many hours, but I think it's the most studied system in the James Webb, and it's impossible to find anything according with that. So it's.
So you
I want to cry.
Okay, so I will say you can look at papers where they simulate observations with JWST for the TRAPPIST-1 system and other M-dwarfs, and they do say, oh, ozone's easier to detect, as in it'll take like 50 transits instead of 500, which I would say is not detectable. No one's going to agree to that. With JWST, honestly, I feel like the most we're going to do is if we can determine if any of the TRAPPIST-1 planets have atmospheres, because it seems like the inner ones, so far it's looking like they don't. My old research group in Denmark, actually, they're working on TRAPPIST-1c data. And spoilers, the star makes everything so, the stellar variability of TRAPPIST-1 makes everything so difficult. I think we're at the point with terrestrial planets where just being able to tell if they have an atmosphere is what we should be settling for.
Yeah.
Maybe we'll see something else, but no, biosignatures will take a long time. It's not, unless we dedicated all of JWST time to say looking at TRAPPIST-1 E or F, which no one would ever agree to, because we want to look at galaxies and other fun things. No, I don't think JWST is going to do anything with biosignatures.
Okay.
The ELT will maybe be able to do some cool O2 and O3 detections. Maybe.
Maybe.
So,
We all have to live long lives so we could see this happen.
so Thea, which is the best system that we can search?
According to this
Exactly. According with this and according with the instrument that we have.
Yeah. I think it's a kind of complicated question because, you know, we all love M-dwarfs when we think about transit spectroscopy because it's much easier. You have a much better signal to noise ratio, but M-dwarfs are, you know, very complicated. They have different activity levels, they have flares, they have a really long pre-main sequence, which would be baking planets in the habitable zone for up to 1 billion years. However, if you want to think about direct observation, so things like the Habitable Worlds Observatory it wants to do, formerly known as LUVOIR, I think we're calling it HBO now. It wants to look at more reflectance spectra and things like that. And if you think about direct imaging of planets, it's better not to go with the M-dwarfs because they're so close to the parent star that the angular separation is really small. So those direct techniques would be better suited for stars more like the sun. And again, we're working with a sample size of 1, but we can say that life happened on at least 1 planet around a sun-like star. So that's encouraging.
But Plato will discover a lot in
Yeah.
a few years.
Yes.
I hope.
I hope so too.
Yeah.
So maybe Plato will also find some good candidates. I don't think there is a best system. I mean, And I think TRAPPIST-1 is a really interesting system that we're looking at right now from the comparative planetology point of view, because we have the 7 planets that all formed in the same environment. So getting a sense of, can we have planets around M stars in the habitable zone that retain their atmospheres? I think that's an important question. But yeah, when we want to look at, direct reflectance spectra, or even one day direct emission spectra, it will probably be better around stars more like the sun, with a larger angular separation between the host and the star.
So, thank you very much, Thea. It's a very nice your presentation, because many of the things you have shown, we are really have been studying here in our department for quite a long time.
Yeah.
So I'm really very happy. But I think we never gave a seminar where we can show all those processes. So I think I'm really happy that you have showed that. So we see all the process that we are studying. I have a question. We have been developing so sophisticated model, climate model, which included everything about ozone, O2.
Yeah.
There is many studies now trying to do the recovery of the ozone, about which is the impact of the solar spectrum.
Yeah.
And so my idea is, why have you think about the developing a new model when we have so far such a sophisticated and very precise model? That, what is the advantage of your model? Why are you thinking in developing a new one where we already have quite a lot of stuff being developed?
Yeah, I mean, I'm not trying to discount anything that's been done on Earth. I use, for a lot of my work, I'm studying results from people on Earth. The result I showed you, where you could see the maximum amount of ozone for modern Earth would happen around 25%, our present level of O2. That was first shown in a paper from 1972 talking about Earth. What I'm interested in here is thinking about it more in the context of biosignatures and what it would be like around different types of host stars. So changing the amount of O2 and looking at that, which was the first step, is now moving on to thinking about how different biological fluxes would change things. Because when I do read earth science papers, like they are, they're focused just on Earth. We're not thinking about, oh, what if there was an order of magnitude more methane or less methane? So I'm thinking more of a larger parameter space there for exoplanets. Although very much honoring the work that's been done on Earth, because again, I've learned a lot from the Earth scientists. And I love working with Earth scientists. You want to collaborate on this. So I'm simply just expanding it more to different types of host stars and other non-Earth-like scenarios. So this is just what I've done so far, but I'm expanding out to more different outgassing rates predicted by geochemical models and things like that. So just exploring a wider parameter space. And I'm using the 1D models in particular instead of the very fancy ones that we have on Earth, so that we can, explore the wide parameter space and not use all the computing time in the world. But I think it's very important that we check our models against each other. And I have a collaborator that does 3D models of the Earth-Sun system and ozone. And showing where they agree and disagree is very important, because my collaborator has really good ozone models for Earth, but in his paper, he'll have 10 models, because that's really what you can afford computationally. Whereas my last paper has, I think, 500 models. So it's just sweeping out the parameter space.
I have one question. You have been showing the level of ozone according to different level of molecular oxygen. So I was expecting that maybe you also show how much molecular oxygen we have seen along the history of the Earth. So have you tried to look at what will be the maximum ozone around the lifetime of the Earth?
Oh, well, that's an interesting
Because that will
idea.
tell us about in which time of the age of the solar system we're looking at, we expect to have ozone maximum.
Yeah, so it looks like it was about over 10% our present level of O2, where you start to have an ozone layer like we have today. So that, depending depending on the geological evidence that you choose to use, because of course,
Yeah.
no one completely
Yeah,
agrees.
I was thinking in the fact that, well, on one
Yeah.
hand, we have a evolution of molecular oxygen,
Mhm.
but on the other hand, we also have the evolution of the star. So
Yes.
so that was my point of view, combining between both,
Yeah,
see which way we would expect to have the maximum ozone at the age of the solar system, of the
Yeah.
planetary system.
and that's another, so there's a bunch of things I want to do in the future, and one of them is thinking specifically about how it changes with stellar evolution for the sun, but also different types of stars, especially M stars at different activity levels. So from the geological data on Earth, it looks like during the Proterozoic, probably from the O2 levels we're seeing, it probably didn't reach about 10% of present level of O2, but it possibly might have. So we might have had an ozone layer as thick as we do right now, you know, a billion years ago. It's possible.
Okay.
Maybe by looking at other planets statistically in the future, we'll learn a little more about our own planet. So I think it's quite interesting. Does that answer your question?
Okay, thank you.
And we could talk more about it later. Anyone else? You can also talk to me later, not in front of everyone, or send me an email. I'll be here for at least 2 years, so.
We have the last one.
Sure.
You have been mentioning about the biosignature of methane and oxygen. Or
Mhm.
the problem is that we know that the methane can be produced by volcanic activity. So
Yeah,
how sure can we be about this particular pair of biosignatures?
yeah, that's a good question. A lot of people have thought about, you know, what could be the maximum flux of methane from just these non-biological sources. So volcanoes, like you mentioned, is one of them. There's a lot of other water rock interactions that could also produce methane. So far, it's looking at like the level of methane you need to have it within an oxidizing atmosphere is much higher than we believe can be produced non-biologically. Of course, we don't know everything, but so far they've done a lot of studies trying to predict not only what is the methane surface flux, but how much will end up in the atmosphere as it's being consumed by the O2. So far people are thinking, from what we know about non-biological production of methane, that if you are seeing methane in an O2 rich atmosphere like Earth's, that flux is high enough to rule out non-biological sources. As far as we know, I'm not a geologist. Are there any, there's no geologists here, right? Cool, I'm the authority right now. That's scary. But so far, we think not. Of course, I think in the future, when we finally can start to see biosignatures, I think it will go down similarly to when we saw phosphine on Venus and everyone disagreed and it was really dramatic. I think that in the end, we're probably not going to see one planet and say, this indicates that there's life there. It will probably be a statistical argument over time, because I think being able to truly tell that something is life and not biological. I love asking astrobiologists this question, is what would you have to see in an atmosphere to convince you that it had to be life? And in the end, people say they need a radio signal from the civilization saying something, because we all study these things, but in the end, we sort of know to really be able to say that it's just life is going to be very difficult. So I know that's a very like cheerful, optimistic thought, but that is probably how it is. It's going to be, if it was easy to find life in the universe, we would have done it already. So.
More questions? Okay. So we have Thea here. You are in building A, B, C?
Yeah, I'm in the
basement.
They said it was a temporary office, but I think they forgot me there. But that's okay. I'm in Dennis's office, if people know where Dennis's office is.
Okay.
So come visit me. I have tea and chocolate that anyone could have, and Band-Aids if you need a Band-Aid. So come visit me or send me an email. Send me your science vision board and we'll talk about it.
Thank you very much.
Thank you. All right, I'll stop sharing then. If I could find my cursor.
So if you need that practice,